This is it, your last chapter of AP Chemistry. And the good news is, you know some stuff. You don't know everything, but from chapter 4, which was the first chapter we covered in the school year, you did learn some things about electrochemistry, and now it's time to apply them. So, electrochemistry has two cases. You can either generate electricity by using spontaneous chemical reaction. Remember, that means a reaction that will happen on its own without any input of energy. Or it will use electricity to make a non-spontaneous reaction happen. So a reaction that wouldn't normally happen, we can give it some electricity and make it happen. But regardless of which case it is that you're dealing with, you have to understand the concepts of oxidation and reduction, which you do know some of it. And remember, we call it redox for short, which is a combination of the two words. So, as a recap, to remind you, we had learned oil rig. Oxidation is loss of electrons versus reduction is the gain of electrons. You can track the loss and gain of electrons by looking at oxidation numbers. If the oxidation number increases, then it would be considered to be oxidation. If the oxidation number decreases, then it would be a decrease in oxidation number, or then it would be reduction, sorry. Here's some examples. Remember, just to recap, if you want to assign oxidation numbers, elements that are all by themselves are 0. So like magnesium here is 0. Oxygen is also 0. Remember, O is always minus 2. So if MgO is neutral, has no charge overall, and the O is minus 2, then the magnesium is plus 2. Remember, the coefficients have no impact on oxidation numbers. So the fact that magnesium starts as a 0 here and becomes a plus 2 means its oxidation number has increased, so it has been oxidized. Versus, in the other example, if you assign the oxidation numbers to each one of these elements, you'll notice that the magnesium here actually goes from plus 2 to 0. So it's going down, so it's a decrease, and so it's being reduced. Remember, if they ask about the agent, it plays for the other team. It's like a double agent. So if it's the reducing agent, it's actually the one undergoing oxidation. If it's an oxidizing agent, it's actually the one undergoing reduction. These are rules to remind you. Remember, any element that is a pure element by itself has an oxidation number of 0. Monatomic ions, so anything that's by itself with a charge, has an oxidation number equal to that charge. Oxygen is always minus 2 unless it's a peroxide, like hydrogen peroxide. In that case, it's minus 1. Hydrogen is always plus 1 unless it's bonded to a metal, like LiH or NaH, in which case it's minus 1. Fluorine is always minus 1. Other ones, group 1A is usually plus 1, group 2A is usually plus 2. And remember, all the oxidation numbers have to equal 0 if the compound is neutral. If it's charged, it has to equal the charge. So, let's practice. See what you remember. And number 1, the oxidation number of hydrogen, because it's by itself, is 0. And number 2, the potassium, even though it's by itself, it's charged. Its oxidation number is plus 1. And remember, in oxidation numbers, the sign goes first, like plus 1. But in charge, when we're writing charges of an ion, we would write 1 plus. It's just by convention. No one's going to take off points if you do it opposite, but I do want to point it out to you that that is the way it's done. Now, when you get a compound like dichromate in number 3, remember, every atom needs an oxidation number. So you start with what you know, which you know on the previous list that O is always minus 2, and then you work to what you don't know. Since the O is minus 2 and there are 7 of them, that's a total of minus 14. They all have to total up to the charge on the compound, which is minus 2. And you have to figure out chromium, but remember, you don't have 1 chromium, you have 2 of them, and you need to figure out what 1 chromium is. So if you add 14 and divide by 2, you'll figure it out that the chromium is plus 6. So for the next one, chlorate, you do something very similar. ClO3 minus, you start with what you know. So the O would be -2. That gives you a total of -6 because you have 3 O's. But because you need the total to equal -1, and you already have -6, then the chlorine must be +5. Then, for the next one, SO3. Again, start with what you know. O is -2. Since you have 3 of them, that's a total of -6. And since you need it to total to 0, then the S must be +6. Now, NH3. Remember, the rule is H is always +1 unless it's bonded to a metal. Now, in this case, N is a nonmetal. That means that the H is still +1. There are 3 of them, so the N must be -3 to total to 0. And the next one, CH3OH. We know O is -2. We also know that each H is +1. However, there are 4 H's. So right now, if you add up the H's and the O, +4 and -2 will total to +2. And the C is going to have to be -2 to total to 0. Then the last one, HSO3 minus. Again, start with what you know. You know the O is -2. You know the H is +1. That gives you -6. And +1 is -5. And you need it to total to -1. So to do that, the S would have to be +4. Now, the reason that we need to be able to assign oxidation numbers is to be able to figure out what has been oxidized and what has been reduced. So, let's try these reactions out. First, assign all oxidation numbers. Even though the Fe is alone here, it's going to be equal to its charge, so it's +2. In the permanganate, start with the O, -2, but you have 4 of them for a total of -8. In order to equal -1, the Mn must be +7. Protons here, since their charge is plus, they must be +1. The irons will be +3. The manganese ions will be +2. And then O is -2 and H is each +1. Now, what you need to do, remember, is look for the ones that changed. So what changed? Mn changed and iron changed. Now, one of them has been oxidized, one of them has been reduced. Now, remember, we always write it in terms of the reactants, what has been oxidized, what has been reduced. So here, the iron went from +2 to +3. Since its oxidation number went up, it has been oxidized. So Fe2+ was oxidized, which means that it is the reducing agent. Now, on the other hand, manganese went down. So manganese was reduced, but we would write it as MnO4 minus was reduced, unless it asks for the atom. If it asks for what atom was reduced, then we'll just say Mn. And then that makes it also the oxidizing agent. Now, in the next one, again, assign oxidation numbers. The O is -2, and I'm not really sure about N or Ag, so I'll pull out the polyatomic nitrate. Since I know that O is -2, and that's a total of -6, then I know the N has to be +5. And then that means the silver must be +1 in order to total to 0. Copper 0, silver 0. The nitrate isn't going to change, whether it's on the left or the right, it's the same distribution. And then the copper, because you have 2 nitrates that total to -1, that means in total you have -2, and since you need the copper to balance that out, it's going to be +2. Now, what happened? Silver. Silver went from +1 to 0, and then copper went from 0 to +2. So which one was oxidized, which one was reduced? Well, it looks like the silver went from +1 to 0, so it went down. But we won't write silver, we'll write silver nitrate was reduced, and silver nitrate is the oxidizing agent. And then the copper, again, was oxidized because its number increased, and it would be the reducing agent. Now, do you remember how to balance these reactions as well? The phrase was eating old hibachi chicken cold socks. Eating means you balance all the elements except the H and O. Old represented to balance the O's by adding water. Hibachi meant balance the H's by adding protons. If you're in acidic, you will only have to do these steps, but remember if you're in base, you have extra steps because protons mean acidic conditions. Chicken, you're going to balance your charge by adding electrons. Cold meant to cancel the electrons, and you'd have to multiply one or more reactions if they don't equal each other. And then sucks meant sum them up. If you're in a base, though, remember, after you sum them, you have to add the same number of hydroxides to both sides as you have protons. The OH and H will make water on one of the sides and then re-cancel on the left and right if possible. So here is an example. I'm going to do one with you to remind you how to do it. And I'm actually going to do the second one because it's in basic conditions. So I'm going to ask that you do the first one on your own, but I am going to give you the answer so you don't have to worry and you can know if you're correct. But you really truly need to do it on your own to get a grip on how to do it if you forgot. So in the end, you should get 5, you know what, let me just do it this way, 5 oxalates, 6 protons on the left, and 2 permanganates. And then on the right, you should have 10 CO2s, 2 Mn2 pluses, and 8 waters. So go ahead and try that and see if you can get it. Feel free to pause the video or do it later, but you do have to have work shown when you turn in your notes. Now, for this next one, let me explain how to do it or remind you. Remember, before you can do eating old hibachi chicken cold socks, you have to split it into 2 half reactions first. Now, you can assign oxidation numbers because 1 half reaction is for oxidation, one of them is for reduction. But truly, assigning oxidation numbers sometimes just takes more time. If you kind of look at the elements, I've got Cn minus on the left, and then on the right I have CnO minus. And then on the left I have permanganate for the other one, and MnO2. So here we go, eating elements. In the first reaction you have a C and an N that's not H or O. I have 1 C on the left and 1 C on the right. I have 1 N on the left, 1 N on the right. I'm good. In the second reaction, the only element I have to check is Mn. I have 1 on the left and 1 on the right. Now, old, oxygen. In the first one, I have no O's on the left and 1 on the right. So I have to add 1 water to provide that O on the left. In the second reaction, I have 4 O's on the left and 2 on the right. So I'm going to have to add 2 waters to make up those 2 extra O's. Now, protons. Hibachi was to add protons to balance the H's. So in the first reaction, I have 2 waters on the left, so I'll add 2 waters on the right, or I'm sorry, 2 protons on the right. In the second reaction, I have 4 H's on the right, so I'll add 4 protons on the left. Now, next, I now need to do charge. This is where most of you would screw up, if you remember. In the first reaction, the charge on the left-hand side is -1 because water's neutral and I have 1 cyanide. On the right, I have a negative on CnO minus and I have 2 protons. So on the left, my net charge was -1. On the right, my net charge is +1. Make sure you don't forget the coefficients. Now, how do you bring +1 down to -1? You have to add 2 electrons to the right. Now in the second reaction, you have 4 protons and a negative permanganate. So net total on the left is 3+, and you have neutral on the right. So I'm going to need to add 3 electrons to bring the left side down to the right side. Now I have to make sure that the number of electrons will cancel. Remember? So now you have to see you have 2 electrons on the upper one and 3 on the second one. Common multiple would be 6. So in the first reaction, you got to multiply everything by 3. And in the second reaction, you got to multiply everything by 2. Now that the reaction has equal number of electrons in both half reactions, I can now add everything up, canceling as I go. So your electrons have to cancel. Clearly they do. There's 6 on the left and 6 on the right. Okay, what else? Waters. Here I have 3. Here I have 4. So the 3 will go away and I'll have 1 left on the right-hand side. What else? Protons. I have 8 on the left, 6 on the right. The 6 go and I'll go down to 2 on the left. And it doesn't look like anything else cancels, so I start to bring down what I have. I have 3 cyanides. I have 2 protons. I have 2 permanganates. And I make 3 CNO minus plus 2 MnO2 plus I'm running out of room, water. Okay, now we're not done. The last step, I gotta make some room here. The last step is you have to add hydroxides. Because you're in base in this particular question, you have to add the same number of hydroxides to both sides equal to the number of protons you have remaining. Since I have 2 protons, I have to add 2 hydroxides to the left and I have to add 2 hydroxides to the right. Now, the water will form on the side with the protons. Since you have 2 protons and 2 hydroxides, they will combine to make 2 waters. Now, that also means there's another round of canceling to go on because I now have 2 waters on the left and a water on the right. So that one's gone on the right and I'm down to 1 on the left. Your final answer after all of this would be 3 CN minus plus water plus 2 permanganate makes 3 CNO minus plus 2 MnO2 plus 2 hydroxides. And you're done. Now, hopefully that was a good reminder of what redox is. Okay, so now let's talk about what's actually happening on redox. Now, this is an example of what you can see with your eyes. In redox, what you would see, this is an example of zinc reacting with copper sulfate. And in the beginning, you see a nice silver zinc bar, and the copper sulfate is blue because the copper 2+ ion, when it's in water, appears blue. Now, what happens? Over time, as you look in the picture, the bar in the solution ends up turning black. That's actually copper. And as you can notice, the solution itself is actually getting less blue. And that's because the copper ions that were in solution on the left side, that were in the water, have been taken out of water, and so now it doesn't appear as blue. Now, this is what we can represent the reaction as happening. We don't see that with our eyes, but this is truly what's happening. The zinc solid is reacting with the copper 2+ ions that are floating around in water, because remember, if it's aqueous, it's dissolved in water, it's split apart. And then what's happening is the zinc, as it reacts, is now becoming zinc 2+, which means it's now aqueous and goes into the water. And the copper, now that was in the water, is now plating or settling as a solid onto the bar of the zinc. And here's a picture of that you can see. It's not the best picture, but it does help. As you can see here, you have lots of water molecules all over, because water would be present in the solution. Here, these are copper ions, these little peachy ones. And then these are sulfate ions. So you've got water in the beaker, copper ions, and sulfate ions. Okay, because remember, when you say copper sulfate aqueous, they've split apart. Now, what's this? This picture right here shows solid atoms of zinc. So this is the zinc solid, and this picture on the left was the copper sulfate aqueous. This is what you're looking at here. Now, as the reaction progresses, what happens? Now look, your solid bar is now copper. You still have water, you still have sulfate, but the major difference is you now have zinc ions in solution, these little white individual ions. So essentially what happened is the zinc and copper switched spots. And how does it do it? Well, it did it by transferring electrons. The idea is that zinc spontaneously lost 2 electrons. Now, remember, Honors 101. when you lose electrons, the atom becomes positively charged. Once it's positively charged, it's no longer solid zinc. And it now has to come off of the surface of the solid, and it goes into the liquid because it's now charged and aqueous. And what takes those electrons? The copper ions in the water are sitting there to receive the electrons. So when the transfer actually occurs, the copper that was positive and dissolved is now neutral and becomes a solid, and the zinc that was solid and neutral now is charged and goes into solution. So they've switched. This whole thing happened with the transfer of electrons, which is called redox. Okay, this video is going to show you at a molecular atomic level, okay, what happens during redox reactions. And I just want to point this out, kind of give you a description of what you're seeing. Right now, what you're seeing are the individual metallic atoms with their cloud of electrons, okay, so that fuzzy ball is the cloud of electrons you see. And what you're going to see is going to get really busy really fast, because remember, around this bar is a solution, and so it includes both of the ions, the positive and the negative ions, and water. You're going to see that as well. And so watch what happens. As it goes, here comes all the water, and you can see just right here, okay, that you have an ion, okay? And now, based on the way the water molecules are facing, you can actually tell what charge that ion is right now. So in the water, you have the big O, which is the red colored atom, and then the two hydrogens are gray. And as you can notice, all the reds are facing that ion. So what that tells me is, remember, in water, it's polar. And the oxygen end of the water is partially negatively charged. So since all the negatives are facing this gray ion, what that tells me, it tells me that this ion right here has got to be positively charged in some capacity. Now, I don't know if it's +1, +2, whatever, but it is positively charged. Now, let's see what happens. Sorry. So you'll see that the gray, oh, it skipped on me. Go back a little bit. Okay, so the gray comes in, and you can see it kind of sit there, and then it's now become a solid. And in exchange, okay, where it is a solid, in exchange on the left-hand side of the screen, you can see that it took one of the previously solid atoms away, and now it's going to take it off into the solution. And then you're going to keep seeing this happen. So then you see it happen again. Nope, there goes the yellow one. Then, oh, there goes a spectator ion. That must be the negative one. Oh, here comes a gray one. Positive ion switches, gains the electrons, and the other yellow, previously solid atom is now an ion and floats away. You can just see it, it's just so busy, but as you can see, just more and more gray atoms are taking the spot of the previous yellow ones, all by the transfer of electrons. Okay. So that is basically what I wanted you to see, and now what we're going to be doing the rest of this chapter is learning how to harness that transfer of electricity or electrons to generate electricity, and then also calculating how much electricity we can form.